Okay, all right. So let me share my screen again. The screen is shared. So there we are. So this is the, so from our discussion then, again, this is the how we declare the tree node. So we have a reference for where the value goes. Then we have a reference for the left child and a reference for the right child. So if you think about it, we have something in here. We have some sort of a key or some sort of value, and then a reference to the left child, and a reference then to the right child. So this is how we sort of create the node for a tree. And what I also have here is a couple of functions just to reinforce the knowledge that we have gained by just working with them on the hand. One of them is just a function that creates nodes. So given a value or a key value, then it will create a node for us. So it will basically, by calling this function, we end up getting a node here with some value, say 5, and then we have the left-hand side being null, and the right-hand side also being null. So that's what we have with this. And then it returns basically this particular node. So we would allocate enough memory for this node, then assign some value, this value, and then assign the left child to be null and the right hand child to be null. The function insert node inserts nodes to a tree. So it will receive the root of the tree and some value. And so maybe I can do this just to make it nice and clear. So it will receive some root of the tree. Let me just, instead of saying node, then see a root here. So that's easier for everybody. So it will receive some reference to the root of the tree, or a pointer to the root of the tree. And once it gets this reference to the pointer of the tree, then it will basically, it will get the reference plus some value. So it gets a value, maybe, the reference, a pointer to the root of the tree, and some value, say 3. And when we call it, then it should basically put 3 in here, and then return the root, which is now 5, basically that. So that's all what it does, this particular value that we have here. Okay, so the idea is that the insert node function is the function that uses the create node function as a helper function, right? So the insert node function uses the create node function as a helper function. And of course, we have seen the pre-order traversal, the post-order traversal, and the in-dot traversal. We have already seen them in the working, and we have seen them in sort of pseudocode area. So we already know what these ones do. So I'm going to go quickly through this, and then we do something else. All right. So say here now we declare a reference to a tree. We say it's null. So we can say we have a pointer called root, and this pointer right now is pointing to nothing. It's pointing to null. So when we call our first function insert node, we are passing whatever is null now this root, because it's null. Remember, we are passing by reference, meaning we are passing the values of the pointers, and then a particular value, for example, 7. So, and then we'll assign that, whatever this gives us, we assign that as a pointer to our to the root references in here. So let's go to that. So this gets called, insert node gets called. So we call it here, insert nodes. And initially, our root here is null, so we are passing null, and say we pass the value of 7 up here. So the first question is, if root is null, which is this, so this is what's going to happen. So at the first instance, the root is null, so this is what's going to happen. It's called a function called create node and passes the key. So it will call this function here, and what does this function do? Allocate enough memory for a node. So it allocates enough memory. Checks whether malloc returns a failure. If it doesn't, then assign the node's key to the value of what was passed. So for example, put 7 up here, and then does left child to null, and then does right child to null. So that's what it does. Right child, left child to null, that. And then it will return the creator node. So this will return to this function the reference to this. So it will return, so it created something called node, node here, which were allocated some memory. So node now points to this, and basically we return this. So maybe the address here was 700. So at the node we have 700. So we return that to, we return this to the calling function. And then this calling function returns that to the main. So the main now will have our root now pointing to this 700 here. And that's how we have 7 as a root of the tree. So that's what is happening. So let's say we pass another one. For example, we pass 3 to it. It's called the insert node. So we come up here and say, well, so we have passed the root. The root now is pointing to 7 to this node here that has the value 7. So we passed 3. So say here was now address 700 has been passed, which is this address of the root. And it checks here if root is null. Now root is not null, so it's not going to execute this. It's going to come up here and say, let's check the key. If key is less than the root key, so the key is 3 that we got, 3 is less than 7, so therefore operate on the left-hand side. So we would say the root left child here, the root left child here, assign it the value by calling this. And what we have said in the past is the assignment operator has right to left association, which basically means that we have to start with the left-hand side, the right-hand side, and then the resultant of that gets assigned to whatever is on the left. So we'll go to this function, insert node. So we'll call, remember this is a recursive function. So we call insert node, we pass root left child. What is in the root left child? Null. So now we are passing null here, and we pass the value, that 3 that we had before. So now we check here if root is null. So the root that is there now is the left child, which is null. So it's null, then create the node. So it will call this function again. That will give us a node that's being made, which has the value 3. And then now this function says when we return that here, it says assign that to the left child. So the left child end up getting 3 up here. The left child gets 3 up here, and so on and so forth. So this basically just operates by, if it was a right-hand side, so for example, say we pass something like 13, it will do the same. It will check, it's not null, 13 is greater than 7, and therefore it will go to the right child, and therefore that will be 13. If 2 comes, say if 7 comes, 7 is equal to 7, so it will not allow duplicates to happen, so the root will happen. So this is basically a BSC tree that shows this kind of things. Okay, now so that's what this insert node function is doing, and that's what the create node function is doing. For the pre-order traversal, what it's doing is just what we have been doing before. We check the base case, and then we print the node, we traverse on the left-hand side, and then we traverse on the right-hand side. So basically, we perform a recursive call using the left child. We perform a recursive call with the right-hand side, and that then is done. For post-order traversal, again, we recurse on the left, we recurse on the right, then we print up the node here. For the in-order traversal, we recurse on the left, we print out the content of the node, then we recurse on the right as well. Something similar to this. So that's basically all the functions, and these are sort of the part 1 from our discussions regarding BSTs, right? Regarding BST. So let's see this in operation. So if we had only these kind of things, it could be easy to operate them. So let me call these. Okay, so call this function here. Sorry, no, this program runs fine, no problem. Runs it with those 3 things, and if you can see, so we in this function here we are inserting. We are inserting them 7, 3, and 13, and then we insert 7, but 7 is not part of it because that is not part of it, because 7 is equal to 7, and we do not allow duplicates to it. When we call pre-order traversal, we get these, we get in order traversal, it sorts them, and post order looks like this. And if we were to draw this tree, like from level by level, then this tree would say, with pre-order traversal, the first item is the root. So here we'll have 7 as the root. And then from 7, we go to 13 in here. Sorry, no, 3. 3 in here. And so what within the traversal, we know this is in the right-hand side and this on the left. And so this is 13. So that's basically what's happening with it. So it works perfectly fine. We can try to make it look maybe more interesting. We could write a for loop and put 10 items and see. So we can put like 10 numbers or something and see how that works. Okay, so let's see. I think we forgot something. Okay, so let's run this. And with this one, it gives it that these values up here. So again, we can draw this tree. If we were to be asked to draw it, we can draw it. We have 7, 49, and all that. So if you remember how we do this, pre-order 7 is the root. Basically means that all the time within your traversal, then it means that all these things are on the right-hand side of 7. The next item we see is 49, so 49 should be here. If we go to in-order traversal, 49 is up here. So from 49 we see 30, that is on the left-hand side, we know that. So if we go here, 30 has on its right 44. On the left we have 23. On the left of 23 we have 9. So that's how it will look on that side. And for 49, when we go to 44, the first item seen is 73. So 73 must be here. And if 73 is here, all these types are on the left-hand side of 73. Which comes first is 58, according to the pre-order. And then 72, and then 72. So this tree this tree looks like this. The one has been generated. And it's a BSC tree. And it's done very, very well. So that's what that code is doing up there. Now, the other bit that we saw was the AVL tree. This is what we created on Tuesday. Again, the code for this is here. Remember, for the AVL tree, what we are doing is, supposing we get some numbers, 7, 3, and maybe 2. 7 comes in, 7 is the root, 3 comes in, we put 3 there. We check what the balance factor is by checking. So the height of 3 is 0. The balance factor of 3 is -1 minus -1. So this is 0. And the balance factor here is 0 minus -1. So this is 1. And the height here is also 1. When 2 comes, we stick 2 in here. Now the height here is 0. The balance factor is 0. If we go up the tree, we go to 3, the height of 3 now is 1. The balance factor now is 0 minus -1, so it's 1. And therefore, the height here now is 2. The balance factor here now is 2. So this tree is not balanced. This is a left case. So we will take this and push it down. So it will be 3 here, it will be 7 here, and it has to be 2 here. So the idea with AVL trees is to perform some sort of balancing, self-balancing as the tree get built. And we have already seen this last Tuesday. And this code actually helps us to achieve this. Important thing here to actually notice, or when you're going through this code to check, the insert node function is exactly similar to the one that we just saw with the tree traversal code up here. The create node function is just the same one. This is a helper function to this one. The in-order traversal is the same. The pre-order traversal is the same. What maybe we have not done is the breadth first traversal, which is basically level by level traversal. So I implemented that over here, the one that can traverse the tree level by level. And then there are these 4 functions here that is helping me to do the AVL balancing. One of them is basically a get height function that given a node tells us what the height of the function is, the height of the node is. Then we have a balance factor function that given a node tells us what the balance factor is, just these 2 things, right? You see a height and balance factor. And then I have this helper function called find max that given the height, say, of the left hand side and the height of the right hand side, I can determine which is the correct height. And I can also do the balance factor with them. And then I have 2 functions here, right rotation and left rotation. Why do I have that? We saw last time that if you have left case means right rotation. We saw right case. Right case means left rotation. So we have those 2 solutions. When we see left right case, we know we have to do a left rotation first to make this a left case, and then we do right rotation on it. And similarly, if we had right left, we'll do a right rotation first and then do a left rotation second. So with only these 2, we can be able to do that work. So the other thing to note is now when I call the insert function here, the insert node function, because I'm performing a self-balancing, I do not do the return node immediately. So if you go back here to the smaller one we had before, we were, because we are not doing much, we're just returning the root immediately once we press the node in. Here we are not doing that. The first thing we are doing, we insert the node, we update the node's height, we calculate the node's balance factor. Remember, we could have saved this value as well as part of this, but there's no point for it. We calculate the node's balance factor, and so we are calculating with the calculated balance factor, height of left subtree minus height of right subtree. That's what we are doing. And we are checking, how do we know that something's left case? We are checking if the balance factor is greater than 1, remember, and the key is less, whatever key that we have, the key that we have been passed, this key that we get, if that key is less than the root left child key, then we know we are going to perform right rotation. This is what I mean. If we had 7 here, and we had 3, and we had 2, something like this. So we will basically track all these things here. And then, so this is 2 here, the balance factor. And once we determine the balance factor here is 2, so if the balance factor is greater than 1, so like this one is 2, so we know the balance factor is 2, then we check whether what kind of case it is. So we check whether the key that we have, so the key we have is 3. So we check, is 3 less than 7? Yes, it is. Then we determine that, oh, this is a left case. So in this code here, instead of also checking the balance factor of the left-hand child, once we determine that this is a left child, we basically simulate that by going in here and checking whether this key's value is less than the key of the node that we have. That helps us to determine whether that's a left case. Similarly, we can check if the balance is less than -1, the balance factor, and the key is greater, then we know we have a right case going to be on this other side. If the balance is greater than 1 and the key is greater, then we know we have a left, then right case, and similarly for right left case. So this part here is determining that. And once we determine that by calling it, we then call this function left case means right rotation, right case means left rotation. So we call those functions. Where are those functions? They are on here, and they work pretty quickly. You know, we just trying to exchange. We have a couple of nodes, so we pass whatever node that we are passing that needs to be to be worked on. So with the right rotation, with the right rotation, we have, so say we have 7 here, and we have 3 here, and we have 2. We know this is the node that we need to be rotating right. We need to be rotating this node right up here. So, so this Y, so node Y here, is pointing to this node that we need to rotate. And then we create a pointer X that points to the right child. So initially this child here is null. So we point this to this child. And then we have another node, T2, that is pointing to node X. Oh, sorry. Node X is node Y's left child. Sorry, okay. So let me draw them from this other so that we can be able to see them correctly and see how the operation is working. So we have a couple of nodes. We have Y, the one we are passing. So this is 7, this is 3, this is 2 here, and this is null on this side. So we have Y. I'm going to draw with like a blue pen. So we have node Y, which is basically being passed here. We have a node X that we now do, and we say this is going to be pointing to node Y's left child. So this is pointing to this child. And then we have something we are calling T2, node T2. And this node T2 is pointing to node X's right child. So this is node X here. Say this one is also null here. So this is pointing to here. We have 3 things that we are working on. And so in order now, so once we have this thing to hold us all the values, which remember what we said, if we had something here and we need a rotation, supposing we had something like 5, let me show you an exact thing so that you can know why I'm doing all that. If we had something like 7, we had 3, and we had 2, and supposing we had 5, supposing this was part of a larger scheme, and we needed to rotate where 7 is, if we needed to rotate this, then it would have been 3, it would have been 2, then it would have been 7, and then 7 would have had 5, right? So that's what would have happened. It would still be like a normal BST tree. So that's the kind of thing we're trying. So that's why we are, because these would become a child of this guy here, then we need to, these are the things which are going to be affected. 1, 2, 3, they're going to be affected. The other side would be 1. So for left case, where we need to rotate left case, we have to be concerned with the node is left child and that node's left child, right child. If we had a right case, then we'll be concerned, say here we have 7, supposing this is 8, supposing this is 6, and we maybe this is something, and so this is not maybe. Supposing we wanted to rotate this by rotating left, then we'll be concerned with this guy, we'll be concerning with this guy, and then we'll be concerned with this guy. So we'll be concerned with the node is right child and the right child's left child. Left case, we're concerned with the node's left child, and that left child's right child. So that's why we have this over here. That's why we have these 3 things going on. Let me move this so that you can be able to see what's happening. So once we establish which ones that we need, once we establish which nodes that we have here, then now, so we have established them now, then we can do a rotation now. Then we can do a rotation now. What does the rotation involve? So we say node X, right child, this node X right child, this one should be pointing to node Y. Remember, node Y is here. So now we have 3's child here, where was null, we have a 7 now. So if we were to redraw this node, this one here, 3, 2 was mentioning to this. So this was null here. And our pointer T2 is pointing to this now, to null. But now this pointer here stop pointing to null, and this pointer now is now pointing to this guy. Okay, maybe I should draw it with a maybe a green pen. So this is now pointing to this guy. Give me. It's no longer pointing to null. So now we have this one pointing here. So that's what that first part does. So node, sorry, no, we are here. So node X, right child. So node X is this one. This right child is pointing to node Y, the 7. And then node Y's left child, is pointing to T2. So node Y was 7. Is right child now, this link now, this link is no longer pointing here anymore. So this link now will point to here, to null, which basically technically means if we were to think about this tree, we have 3 here. The 2 has not been affected. The 3's right child is 7. 7 right child is null. Right? And nothing else gets affected. So that's how the rotation is working. See how cool it is? The rotation actually works. And once the rotation works, we update the heights for the 2 children which are for node X and node Y. The 2 children that have been affected. This one that have been affected, and the node Y, this one, yeah. So this one and this one, because they have both been affected because they've transferred the spots. And similarly, we do that with our left rotation, right? We throw the first one, the right child, and then the left child, and we do the same. I would encourage you to look through this code. The code is available on Blackboard, or if you need me to send it to you, I have it. And then you can look through it and you can run it and see how well it works. So, so that's basically it. And then the other thing, of course, is the level by level order. We should print these nodes level by level as well. So we can take an example. So of course, if I do with this example, this is quick and easy. And then we can take with the other one that we had before. So this tree is called the AVL something. Okay. So with this one, okay, it has printed level by level. If we are just thinking about level by level, at level 1 we have 3, and then level 2 we have 2 and 7. So we have 2 and 7 like that. So this is actually a balanced tree. It's very well balanced. We have 3 and 2 and 5, and we have these pre-order traversals that have been printed out. If we were to do it with a bigger tree, like the one that this code that we had before, let me just copy it and paste it that side, like this one. Let's do this one. Where is it? Okay, actually I had it before here. So I can remove these ones, and I had it here. Okay. So that's basically what we have here, and so let's see. Again, we run it now. Do that, And we have this. Okay, so let's see the difference actually now that we have it here. Let me move these guys. So initially, we had this one. Was it the same one? Okay, we need this one. We need this one for when we were calculating the BST. And this one showed us, let's draw this tree. These are normal BST. This is a BST without AVL. This is a BST. Let's see what happened. With this one, our root was 7. And then we had 7 was followed by 49. Basically, 7 did not have anything on the left-hand side. So we could ask what read that link. And we could say 7 is here. 7 had 49. And from 49, we had 30. And from that, we had 23. From 23, we had 9. If you do not know how to do this, you can ask me a question via chat there. I'll be happy to help you. Yeah, you can do that. And this one had 73. We had 58. And we had 72. And we had 78. So this is how our tree was with the BST. Now let's see how the AVL produces this. Now the same tree with the AVL. If you look at these both things, they have the same numbers, by the way. Same numbers everywhere, exactly same numbers. So let's see how does this AVL with self-balancing, how does it place it? Well, good thing is I already printed them level by level here. So that's nice. We know every level we can have, level 1, we have only 1 node, so 49. Level 2, we can only have 2 nodes, so we have 30 and 72. Level 3, we can have 4 nodes. Yes, we do. We have 9, we have 44, we have 58, and we have 73. The last level, we have 3 things. We have 7, 23, 78. So we know 7 will be here, 23 will be here, and we have 78. So this will be here. Okay, and we're done with it. So if you look at this tree, this one has, if you go back to our conversations with AVL, this produces some sort of symmetry, right? It's very symmetrical in nature, right? This is very sort of symmetrical in nature, achieved by just doing self-balancing of the tree itself. So that's quite cool. And that code that I showed you is the code that's able to produce that. Are there any questions for me regarding that phase of learning, regarding AVLs and regarding BST trees? The second exam is going to be next week on Thursday. So 1 week from today, the 22nd. I intend to cover the materials that we have, AVLs, BSTs, binary trees, all the stuff that we've been covering, plus the materials of the heaps. So we are going to now, starting now for the next 30 minutes or so, discuss heaps, unless there's somebody who has a question for me. So course 5 is basically cover AVL, all AVL things, anything that you can think about AVLs, that's what it covers. So quiz 5 is on AVLs, quiz 4 is on BSTs. Any questions for me? All right, so let me bring up a different screen now. We can talk about this again a little bit. So far, what we have seen is a way for us to create trees. And these trees that we created were achieved using some sort of double linked list kind of style, right? This is what I mean by double linked list kind of style. We had, so double linked list kind of style. We had some nodes. Okay, so this is what I mean by linked list kind of style. We had a struct node. We had a struct node. And that struct node had some int, num, or key. And then we had some sort of reference. to the left child, and we have some reference to the right child, etc. Right? So that's what we had before. So I'm saying that it sort of mimics this idea because we have that, you know, left child and right child and all these kind of things. So that's what we had before. Okay. Now, but we said in the beginning that, well, we could actually do this with an array, right? We could do this with an array. Now, so I'm going to ask a couple of things. So if we had the same thing that we had before a few minutes ago as an array, that would be interesting to have, right? So if we had this number 7, 9, 13, 14, I don't know, maybe 44, 49, 60, you know, whatever, 2. If we had these things in an array, how can we correctly map them into an array? How can we correctly map these things into an array? Okay, so well, we could decide that if this was index 0, then index 1 and index 2 are children of index 0. And this one here, I'll just write here, this would be, supposing this, let me call it K0, this K1, this K2. This child here could be a child of K1. So this will be the first child of K1. And this will be the first child of K2, sorry, K1. This will be the second child of K1. Then this will be the first child of K2, and this will be the second child of K2. So this being K0, K1, K2. Basically, this is what I mean. We have 7, we have 9, we have 13, we have 44, we have 49, we have 60, and we have 2 up here. See that? So we can do that. Actually, one of the things is if we are given an index of anything, we can be able to trace it here, right? We can be able to trace it to what the parent is. For example, say we get something like this guy here, 2, supposing here we get 4. So 4 is possibly here. How can we know that 4 is really a child of these guys? So this index 0, index 1, index 2, index 3, index 4, index 5, index 6, and index 7. How would we know that the guy at index 7 whose parent is? We could do 7 minus 1 divided by 2. And this will be 6 divided by 2, which will be 3. And therefore, index 3, this guy 44, is a parent of 4. And we're able to do that. So we know to know the index of parent equals child index minus 1 divided by 2. That will always tell us that. And once we can know always the index of the parent, then we can equate to which child, you know, to which child belongs to who. so and so on and so forth. So we could do this. Although then the idea then, we could then put our things into a tree. But then, of course, we'll need to have this tree as what? You know, between so last time we discussed the idea of full trees or almost complete trees. So in order to have the tree being put in an array, what kind of tree would it be? So remember what we talked about? We talked about full tree. Who can remind me what full trees are? Full binary tree. Okay. So with this, sorry. So this one we say each node has exactly 0 children or 2 children, 2 child nodes, right? So each node has exactly 0 or 2 child nodes. So that's full binary tree. then we have, so the full binary tree, each node has exactly 0 or 2 child nodes. For almost complete, so the structure now, almost complete or complete binary tree, all nodes, all levels of the tree, all levels are filled up, fill up, okay, with sometimes the exception, of the last level, which when it's not filled, all nodes are on the left. All nodes must come from left to right, from left to right. So that's what we say. So, well, this then, you know, for us to make a tree into an array, then our tree must be almost complete, or complete, or almost, or complete. So we can actually conclude that and say, for tree to be implemented in an array, to be implemented as an array, it must be complete, almost complete. And that's important, right? Because once it's complete, or once we know that the tree is complete, then we can fit it to an array, because no single spots or cells or indexes within the array will go without, right? Okay, not any single one of these things will go without. So that's an important actually thing to do. So if we were to implement trees, that's something we want to do. Okay, so let's go to something else now. So we have learned all this, that's good. So let's go back a little bit and learn now something else. So initially we saw this idea of queues, right? We saw idea of queues. And we say queues were what we call fast in, fast out items, right? Fast in, fast out items. So whatever came fast, supposing we had them as an array, if we had 4 will be served first, then 5 will be served first, 6 will be served second, you know, like that. So this index 0, index 1, index 2, index 3, index 4, and these guys will be served. Index 1 will be 0 will be served first, then index 1, then index 2, and so on and so forth. Now, imagine now that these values that we have here, let's imagine now, if these values we have here do not specifically means the order of arrival, but these numbers means the priority of arrival. So imagine that you have gone to a bank to do some work, and then you get a ticket, and that ticket says, oh, M1, and then you get a ticket says P2, somebody gets another P2, L4, M6, you know, supposing you get this kind of ticket. Of course, we mean that this ticket means something, right? So you could have arrived and you got a ticket called M1, and Ethan arrived and had a ticket called P2, and so on. People arrived and had this ticket, and these are the guys who first came, and then all of a sudden, oh, this guy gets called, the guy with L4 gets called to be served. So you'd imagine then that these numbers means some sort of priority, right? It means like, oh, this guy has higher priority than these guys, etc., right? Correct? Do you understand this? So on a normal queue, the order that you arrived is the order that you get served. In a queue that follows some priority, then the priority of those items is what gets served, right? So let's take another, you know, quirky example. You go to a doctor's place, or you go to a bank, you key in whatever you want, you get a ticket with a number there, and you sit down with a number. So let's imagine that people are sitting on some chairs. So different chairs here. The chairs, let's imagine that this block is like a form for chairs. So that's chair 1, chair 0, chair 1, chair 2, chair 3, chair 4. So the people are sitting on chairs. So the first person comes and gets a number like 19. And a person comes and gets a number like 4. Another number comes, gets number 16. Another person comes, gets a number 4, 3, maybe 4 as well. Another person comes, gets a number 6. Another number comes and gets number 2. So everybody is holding their numbers, and there's no way of determining these numbers. And let's imagine that the person with the lowest number should be the first person to be served. So this person arrived last, but this should be the person to be served. If the doctor is here or the banker is here, this person doesn't know who needs to be, this person doesn't know who actually has the lowest number. So the first thing is, what would this person need to do in order to know which person has the number? Of course, the easiest solution is, of course, ask the people, right? Ask the people. So you ask this person, the first person, oh, what's your number? The person will say 19. Okay. Then says, oh, and you possibly write it down somewhere. Said, what about you? The guy says number 4. So now this person knows, oh, this person has the lowest, value. And then ask the other person, oh, 16. Okay, this little person has 4. Then ask this one, oh, I have 4. Okay, so it's, oh, these two guys are on the same level. Then ask this guy 6. Oh, okay, these two guys still have the same level. Then ask this guy says 2. So these guys lose their level, and these two persons want to be served now. So if we were to think about this for a few minutes, let's think about it for a few minutes. If we were implementing something, so this is a queue, we'll call this kind of queue a priority queue. You know, you are being served based on some priority. Okay, so if we had this, now this looks like a normal array, so I'll just call it unsorted array because it's not sorted. Things are just the way they are, unsorted array. Now, if you have sorted unsorted array like this one, to serve somebody, I will share like these are serving. So we have serving somebody, and we have serve somebody, and here we have serve, and here we have add somebody to the queue. Add to the queue. So if we, and I want you to think about this for a few minutes, right? If you were serving somebody, so all these things have been queued up, and you need to get the lowest rank per value, then you have to compare everyone's ticket. So you compare this one with this, compare this one with this, and you keep comparing until you find the person with the lowest value. So to serve somebody means we compare all the items to get the person, and then we serve them. Could you write on the chart and tell me what time complexity does that take? How many comparisons would we have to do to make sure that we get the person with the lowest one? Yeah, we have to do 6. So we have to do 6 because there are 6 items in here. So if we had n items, it means we'd have had to do n comparison to get the person with the lowest one. So we can say to serve is big O of n. N meaning how many comparisons are we going to do? We're going to do as many comparisons as the number of items in there. So we say the big O of n. At the worst case, to get the person with the lowest value or the lowest priority, then it's O of n. Okay, what about adding someone to the queue? What would be the time complexity of adding someone to the queue? So supposing there is another space now here to add somebody. What is the complexity of adding somebody to the queue? What do we need to do? So if you're looking at this, it's just go to the head of the queue and add whatever. So I'll come to the head of the queue and just put an item there. So adding to the queue is nothing. You just go to the head. This is a normal array. Imagine a normal array that you have where you add item at the back or the open index at the back. So you're just adding at the back there. So adding to the queue is O of 1 because you don't need to do anything, right? Somebody comes to the bank, they just go to the ticket machine, puts on the ticket, so goes to the bank, puts in a ticket. I have to Okay, goes on, puts on a ticket, and then that's it. What about, so that's for done. And if you think about this, if this was a linked list, again for the linked list is the same, right? If we wanted to know the person with the lowest value, again it will be O of n to get the person with the lowest value. Basically, we have to create a while loop. We need to create a while loop to get the person with the lowest value. To add somebody to the queue, again, this will be O of 1 because we just need to do insert head, so that we can always insert at the beginning. So what happens when it's a sorted array? Sorted array, or even a sorted linked list. Sorted array or sorted linked list. So by sorting, this is what I mean. So supposing we have this, so lowest would have been here, 2, 4, 4, 6, 6, 7, 16, 19. So if we want to serve the person with the lowest priority, what do we do? If we want to serve the person with the lowest priority? This is a sorted one. Well, with a sorted one, the lowest priority, if the lowest priority is the first person to be served, or the person with the lowest value is the first person to be served, so we'll just go to the first index and get whatever is there, right? Correct? Yeah, we'll just go to the lowest index and get that person. So serving somebody will be O of 1. Basically, imagine that the teller in the bank, we just look at the front of the queue and knows that whoever at the front has the lowest index and just calls them, hey, you come, you get served. But what happens when we want to add a new value to this queue that's already sorted out? What happens when we want to add an item to the queue that has been sorted out? So I'm going to draw it the other side, and therefore you can tell me. So this queue looks like this, or this array, 2, 4, 4, 6, 16, 19, or something like this. So it looks like this. What happens when we want to add a new item? What happens when we want to add an item? Say somebody comes in and they get 1. So 1 should be in front of 2. So what should we do? What's the easiest way to do this? Someone? Insert them in the front. So if we insert them in the front, what will happen to 2? Remember, inserting them in the front means just remove the 2, right? Yeah, okay. So Ethan has a very good answer. He says, add them to the back. We add them to the back. We add 1 to the back, like that. And then what we're going to do is simple. We just keep comparing with the things in front of us. We say, is 1 greater than 19? Remember, by inserting the back already, now we have created a space. Is 1 greater than, less than 19? Yes, it is. So 19 will come here and 1 will come here. Is 1 less than 16? Yes. So 16 will come here, 1 will come here. Is 1 less than 6? Yes. This would be that. Is 1 less than 4? Like that. Then 2, and then the space will be for 1. So the first question I then ask is, remember, so here we are performing a sorting, right? And sorting requires comparison plus swapping items. So it's comparisons plus swapping. So how many of them would we need to do here? Just to add 1 item, how many of them will you have to do? I think there are going to be equal number of comparisons with swaps. But how many of them are there? If we had n items, how many of them are we going to do? Yes? How many of them are going to do? 6. So we're going to do 6 of them. So if we had n items, so we'll have to do n. We'll have to do n of them, which basically means to add an item to an already sorted array, is really big O of n, because, well, we have to really find the spot where that thing will be. So in our case then, sorting out the array is O of n, sorry, adding an item to a sorted array in order to create this priority queue is O of n. The same for the linked list is O of n. So if we, so the first, of course, now we established things, right? We are trying to make a priority queue, or how we queue items and then serve them with the order of priority. We have seen 4 ways, 4 techniques. If we use unsorted array or an unsorted linked list, adding items is easy, is O of 1. Serving them or dequeuing them is O of n. If we implement this sorted linked list, this priority queue using a sorted array, then, well, removing an item will be O of 1 because we know exactly where to go to remove them. But adding an item becomes O of n because, well, we have to do them at the end, and then we keep checking and we keep checking until we find the correct positions they are. So we are sort of like in 2 extremes here. We either choose one of these techniques and then we'll be serving at O of n and adding O of 1, or we choose one of these other ones where we serve at O of 1 and we add at O of n. So the question that then remains is, can we do better? Can we be able to implement maybe the word implement can be written here. Can we implement a priority queue, okay, that is more efficient, in terms of time complexity, it's more efficient. So instead of O of n or O of 1, can we have 1? Now, we know one thing about trees that we have been seeing. We know with the trees that we had, we were adding items with O log of n. We were searching for items. Okay, so let me see here. With the trees, when we had trees, binary trees, we were able to add, we were able to remove, we were able to search, and we performed all these things with big O log of n, right? That's what we did. So to add, to remove, to search, we did this with O log of n. So the question is, can we be able to use, can we use a tree? Maybe that's one. Can we use a tree to do this? Can we use a tree to do this? And the answer is yes, we can do that. Yes, we can use a tree to do this. Okay, we can use a tree to do this. We can add item and be able to do this. So we can use a tree to actually be able to do this, to add, to remove, to search with O log of n. The question is how? So the answer to that question is we can implement something that we call heap. Okay, we can implement a heap data structure to do this, heap data structure. So the next time we meet, we are actually going to be talking about this heap data structure. But this is what we are going to do. I am going to create another video, which is going to be posted here and on Blackboard. And that is going to explain and talk about heap data structure. When that is done, I'm going to post it to you to tell you to look at it, hopefully between today and tomorrow. So you'll do that. I'll also post a quiz called Quiz 6 that will also talk about heaps. And when we meet on Tuesday, instead of relearning the materials, we're basically going to work on examples on heaps. And that should be able to conclude our discussion with it. So the most important thing is this motivation. Like, okay, if we wanted a priority queue, how can we go about it? And we say, well, there are 4 ways really we can go about priority queue. Unsorted array, unsorted linked list, both of which would serve with O of n and adding with O of 1. Or we can do a sorted array or a sorted linked list, which will go at O of 1 and add at O of n. And we are sort of stumbling through these 2 extremes. So to solve that problem, can we implement this with the more efficient ways? we know trees are working with O log of n, or binary trees rather. Binary trees. So with binary trees, we saw these. Can we utilize this idea of a binary tree to do a priority queue? And we said, yes, we can do that. And that answer will be given by what is called a heap data structure, which is basically an implementation of a binary tree as an array that keeps items in priority. So that is what the video is going to be about, or the new lecture video, and then a quiz regarding that, and then we practice on it when we meet next week. Are there questions for me? I'm going to stop there.